Welcome to Brain Vision.
This is a very interesting question. We have L1 and L2, and these two wires are made of different material. One is alumina and one is steel. And we hand a mass of 10 kilograms from like the end of these two jointed strings, and we want to induce want to have a standing wave on the string so that the is a knot. So let's first think about what the standing wave would look like. Apparently, there will be some standing wave. I'm just drawing for reference as an indication. Don't take any periods I draw as. Maybe we can have some of here. We can maybe have some of here. Then the thing is, the joint better stay stable. And is that because alumina and steel have different mass density. They have the same tension because the same tension induces per kilogram mass, but they have different, so they will have different velocity, and because of that, the wavelengths may be different on these two sections of the wire. So let's first calculate the ratio of the velocities. So let's think about it. We have rho, we have area. This is area, area, and we have, and these two will have to give us a mass density, and similar over here. For steel string has a section. So we can find the velocity difference, the velocity for the aluminum string and the steel string. And then, how does that velocity connect to the wavelengths? Let's write out L. Let's say it's like the length of, it can be L1 or L2. So L is lambda over 2 times n. And lambda is V over F. It's V over F. So we have, other words, we have frequency equals NV over 2L. So that's true for both the aluminum string and for the steel string. And the frequency has to be the same for both sections. Why? Because it's the same wave. If they have the different frequency, if you think about it, if this green wave oscillates 5 times while the blue wave only oscillates 3 times, it's not going to be a continuous string. It's a joint. It has to be a very continuous point. It can only have one motion at this joint. So because of that, the left and right have the same periods. They have to have the same oscillating frequency. So what that means, 1 V1 over 2L1 has to equal to N2V2 over 2L2. This is a boundary condition we have between the aluminum string and the steel string. Okay, so now we need to really plug in what the velocity is, because we know what L is, but we don't know what velocity is. So velocity is tau over mu. Tau is, and mu is rho times cross. Because why is this so? Because mass total is rho times volume. So linear mass is like rho is total mass over L. So total mass times volume over length is total mass times area. So that's rho times 8. So okay, So this is the formula we have. If we plug it back, we can find the ratio of n1 over n2 plus 1 over n2 equals v2 over L2 over v1 L1. mg is the same for both of them, so it goes, and a is the same for both of them, that also cancels. Only left with L1 over L2, rho 1 over rho 2. Okay, so that's nice because we got rid of all those weird numbers. We don't have to deal with them anymore, they just cancel. Then we can plug in the numbers: 60 centimeter, 86.6 centimeter, rho 1 is 2.6, rho 2 is 7.8. What is n1 over n? It is 0.4. So it's 2 over 5. That's like the smallest integer. The smallest integers is n1. Excuse me, n1, and n2 equals 5. And doing that, the tension that is provided. So the tension, our final goal for part A is to find what is the lowest frequency. And as I said, the frequency will be the same for both left side and the right side. So we only need to find out one of them to find out what the frequency is. And we already have this formula. So we can go back to that formula now that we know what n is to find out what the frequency is. So frequency equals 2 times C is over rho A, mg is 10 kilogram times 9.8 meter per second squared. Rho is 2.6 grams per centimeter cube times 10 to the negative 2 centimeter. And this is centimeter, so I also have to this to meter. 1 centimeter over 0.01 meter. Sine over 2 times L is 0.6 meter. Okay, put everything into the calculator. It turns out to be 324 hertz. And that is a frequency for the wave. Alright, so that's for part A. And now let's look at part B. Asks what how many nodes are observed at this frequency. Okay, we already say this is luminance, this is still. We know that for left hand side 2, so it's going to be like something. In right hand side n equals 5, so like 1, 2, 3, 4, 5. Excuse me again. And how many nodes do we have? We have 1, 2, 3, 4, 5, 6, and we need to count these two as well. 8 nodes